Okay, now up till now we've been talking about inheritance and we've been kind of ignoring um, one of the keywords that shows up very prominently in inheritance, and that's the public keyword. So let's talk a little bit more about that. Public inheritance. What does that mean? Um, what we're going to find that it means is that it describes a relationship that we tend to call the is-a relationship. Okay, so whenever we specify the inheritance relationship, we'll say something like class square inherits publicly from rectangle. Public inheritance means that other code can see what square inherits from. And this lets other code know that square, in fact, is a rectangle. Square is a rectangle because square inherits from rectangle. Inside of square, there's a rectangle, right? And this turns out to be a very important implication for C++ programs. That implication is that wherever we need a rectangle, we can use a square. And let me show you this. One implication of that is that we can kind of use the base type to refer to the derived type object. So let's say I have a square called S, and then I make a reference R of type rectangle. Well, because a square is a rectangle, a square inherits from rectangle publicly, a square is a rectangle, then I can set that reference equal to S, and this is perfectly allowed. It looks weird because they're not the same type, right? Squares and rectangles are different types. But because square inherits from rectangle, publicly, the compiler knows and is allowed to use the fact that a square really is a rectangle. And that means we can reference a square as if we're referencing a rectangle. And so this reference R equal to S is perfectly legal. And then down here, I can even call the area function, which is, a function contained in rectangle, and calculate the area and print it out. So not only can I refer to S, but then when I try to call member functions on S, then this is going to work the way I would expect. So that's pretty neat. I can treat a square as a rectangle because of public inheritance. And not just with references, I could also use pointers. So if I put a new square object on the heap, then I could actually take a rectangle pointer and set it to point to that square object. And just like before, I could use that rectangle pointer to call the area function and calculate the area of the square. So pretty cool. So since square is a rectangle, then I can use a rectangle reference or pointer to refer to a square. However, yeah, and actually just one other point. This is not a cast. The S object isn't being converted to a rectangle. The S object here, the square that I created, it stays a square the whole time. It's just that because there's a subpart of it that's a rectangle, for a little while we can pretend like it's only a rectangle. And we'll just be able to, now when we have a pointer that's a rectangle type pointing to a square object, there are some constraints. I can only use the rectangle parts of a square. I can't use any additional parts of the square that are different than rectangle. Only the parts of the square that are the same as the rectangle are accessible. And that's the reason I can call the area function. It's because area came from rectangle. It's a part of rectangle. And so when I'm using a rectangle pointer, I can call a function that's a part of rectangle. But I can't necessarily call things or use things that are only a part of square and not also a part of rectangle. Okay. However, the converse is not true. Rectangles aren't necessarily squares. And so if I make a rectangle and then try to make a square reference to refer to that rectangle, that's a syntax error. Because the compiler knows that a rectangle is not a square, right? And every kindergartner knows that. A rectangle may not be a square, but a square is a rectangle. The other way works, but this way does not work. Okay, so this brings us to the is-a relationship and kind of more formally talking about the is-a relationship. So derived classes share the is-a property with their publicly inherited base classes. So since square inherits from rectangle, that means square is a rectangle. And what that means practically in our code is that we can use the base class type to reference or point to derived class objects. It's very important to clue into this reference or point. I'm not saying that a rectangle, that a square object can be referred to as a rectangle. I'm saying that we can use a pointer or reference to refer to that square object, okay? A rectangle reference or a rectangle pointer can be used to refer to a square object, right? So this is really important because what it means is that I can have some base type like rectangle that could point to rectangle objects or square objects. And so if I want to write a function that might take a square or a rectangle, I don't have to write two versions of the function. I can write one version of the function that takes a rectangle reference. And then I can pass into it either a square or a rectangle, and it will work. And so that's pretty useful. That's a pretty useful feature. There are kind of three common use cases for this is-a relationship. And actually probably even more than that as we go along. But as a way to get started, and I think we can pinpoint three cases where is-a kind of shows up and is useful. So we can reference an object using its base class type, reference or point to an object using its base class type. That's what I just showed you on the slides, where I say, let's declare a rectangle reference and point it to a square. That means I can just pretend like that square object is a rectangle for all practical purposes. That's pretty neat. I can point to an object using a base pointer type. And then I can also pass or return an object to or from a function using its base type. And it is worth pointing out the compiler does see this as a conversion when it comes to function overloading, but it allows me to write code in terms of a base type and then have that apply to all of the derived types. And so that can be pretty handy in terms of keeping code small and keeping code simpler. I don't need different versions of functions for all my derived types. I just need one version of the function for my base type. And just to kind of illustrate that idea, here's a little example. This is function overloading reloaded for the case of inheritance. So I have three different function declarations. I have a function that takes a w and an integer as an argument. I have a function that takes an object x as an argument, a reference to x, and I have a function that, a function that takes a reference to y as an argument. So I have these different classes, y, x, and w. And what I'm asking you to assume is that x is a w. In other words, x publicly inherits from w. Okay, and then I have these variables declared somewhere. Little w is a w, little x is an x, and little y is a y. Okay, now which function is going to be called in each of these cases? So here I call f with a w. Okay, and when I look over here at my candidate functions, there's only one function that takes a w, and that's this first one. And I can, the second argument can take a default value. Okay, so that means since any other function would require a conversion on the first argument, they're not a good match. And so I'll call version A here because this W object will match this W reference. That's the first argument, so that's going to be the best match. The second case, I call F with object X. Now, here's an interesting thing. X is a W, okay? And so what that means is that it matches the first argument of this function, but that takes a conversion because I would have to convert X to its base class W. So there would be one conversion there. Okay, but B expects a reference to X, and that requires no conversion because it's a direct match. So here I would call function version B. A is a candidate, it's just not as good of a candidate. B wins out because of fewer conversions. Okay, function 3, I pass in an x and a 1. Now here's an interesting thing. This takes 2 arguments. There's only one function here that can take 2 arguments. So really, function A is this first function is the only possibility. Now the question is, does it work? Well, we know that x is a w. So this little object x can be converted as into a reference to a w object. It costs a conversion, but since this is the only possible function, since we're able to convert to it, we have to do it. And so the compiler will do that conversion and call function A. Let's say we call f with w comma 1. Well, here again, there's an exact match. A is an exact match. It has 2 arguments, so it's going to call A. And then this last one, we pass in object y. There is only one function that matches, and so there's only one good candidate, and it's going to call function C. Okay, so hopefully that helps make a little more sense about what's happening with public inheritance. Public inheritance basically says to the world that, like in this case, x is a w. And since x is a w, anywhere we need a w, we can pass in an x. And anywhere we want to manipulate a w using a pointer or using a reference, then an object of type x is a good stand-in for an object of type w because x is a w. And this idea of is going to show up in a lot of places and get used a lot in some of the code we write for the rest of the semester. So it's a very simple idea, but it turns out to have some pretty big implications. Okay, so in summary, derived classes share the is-a property with their publicly inherited base classes. And we can use the base class type to reference or point to derived class objects. This is really handy for function arguments, pointers, references, and things like containers.